Hi, my name is Yuran, and I am presenting Surface I/O, creating devices with functional surface geometry for haptics and user input. This work was performed by myself, Craig Shultz, and Chris Harrison at the Future Interfaces Group at Carnegie Mellon University. Some would say we have reached the era of ubiquitous computing, with the proliferation of computing devices in our everyday lives. Interacting with our devices, however, has still remained largely constrained to two dominant types of interfaces. First are seamless, continuous surfaces, most often flat, with touch sensing, such as membrane keyboards on microwaves or touchscreens on smartphones. Second are interfaces comprised of mechanical inputs, typified by mechanisms like buttons, sliders, and dials. While touchscreens offer a seamless, robust, and reconfigurable platform for designers to tweak and test, they lack tangibility. Conversely, mechanical interfaces offer great tactile affordances, but they can be difficult to design, implement, and adjust at scale. Instead of the wholesale removal of tactile components from interfaces, we explore an intermediary approach which we call Surface I/O. This approach functionalizes the exterior surface of devices, allowing them to offer haptic affordances without dedicated mechanical components, while simultaneously enabling user tracking. We envision Surface I/O not necessarily replacing more traditional touchscreens and buttons, but rather being designed into existing surfaces as a way of imbuing additional functionality with minimal additional cost. Our system utilizes three scales of surface geometry working together: macro, meso, and micro, drawing on prior work in psychophysics, industrial design, and HCI. First are macro-scale surface features between roughly 5 cm and 1 mm, which create discernible static deformation on fingertips, such as shape and edges. In this example VR slider, we have a valley that captures the finger in a track-like feature, as well as small vertical lines that act as detents. At our meso-scale, between roughly 1 mm and 200 micrometers, repeated features can create textures that can be felt when translating a finger across the surface. In this example, we use rough textures to demarcate the end of the slider. Finally, micro-scale features below 200 micrometers cannot be readily felt, but create vibrations that can be sensed and used to drive interactive functions. We attached a small piezoelectric disc to sense the vibroacoustic signals. Here's the signal of an example application as the user swipes her finger on a VR headset. Note that we use different ratios of smooth and vibratory textures punctuated by detents in order to track the position of the finger. These surface features can be mixed and matched, as well as overlaid with one another in order to create functional objects. Surface I/O can bring particular value to applications where the visual load is high and components must be durable. Here you can see a figure of our Surface I/O augmented steering wheel. A features a closer view of our 4-way directional control made out of 4 teardrop finger wells. C features a closer view of a small spiral dial where thumb controls could be used, for example, to navigate among a series of modes. Surface I/O could also simplify designs, such as the multi-material and multi-process mechanical buttons on this Alexa Echo, with an entirely solid and inexpensive single piece of plastic. Importantly, once prototyped using 3D printers or laser cutters, these interfaces can be manufactured at scale using methods such as injection molding or stamping with very low and essentially no additional component cost for consumer goods. We designed a series of studies to investigate a core set of research questions. Our first study focuses on design primitives and if they can be discerned by a user, express specific tactile qualities, and offer any intrinsic affordances. We created a representative stimuli set containing surface primitives ranging from macro to meso-scale, covering textures, locating features, and guiding features. Participants were interviewed open-endedly about their pleasantness and impression. Subsequently, participants were asked to rate the textures on a 5-point Likert scale, evaluating the tactile forms, including roughness, stickiness, bumpiness, and sharpness, from questions 6, 7, 8, and 9. Participants then rated on tactile signifiers, including continuity and movement affordance, question 10 and 11. Finally, they rated on the overall tactile impression, including intensity and pleasantness, question 4 and 5. Our second study focuses on functional associations. We combined primitives into basic widgets, which were presented to participants in thematic sets, exploring different design facets such as the geometry of locating features, size of locating features, detent versus heels, effectiveness of detents, geometry of guiding features, macro versus meso guiding features, etc. We included open-ended questions as well as Likert scale ratings evaluating the efficacy of conveying function, such as complexity and intuitiveness. We synthesized the interview result and Likert scale ratings from Study 1 and 2 to form a set of design recommendations. These design recommendations covered how to design effectively for pleasant interactions, conveying axes of motion, point of interest, widget-like sliders, buttons for different control functions, such as for continuous or modal changes. For more details, please see our paper. As a proof of concept, we performed an input accuracy study that quantifies the classification accuracy of 4 distinct microscale features used for input tracking. You can see the experimental setup on the left. Using a leave one participant out cross-validation procedure, we found a mean texture classification accuracy of 90.1%. While there is room to improve accuracy, we believe this initial result demonstrates the feasibility of our input sensing approach. We evaluated the baseline resistance to wear of our microscale surface I/O features, because our larger meso and macroscale features should only be more durable and reliable. We selected 7 common product materials that could adopt surface I/O designs in the future and simulate user wear using an artificial finger probe. After roughly 240,000 swipes, no materials demonstrate visible signs of abrasions under microscope, and all materials preserve identifiable harmonic vibroacoustic spectra. To summarize, we propose and articulate a framework that entails 3 scales of surface geometry, macro, meso, and micro, to functionalize surfaces for rich haptics and sensing, drawing on prior work in psychophysics, industrial design, and HCI. We present a workflow in the design and manufacturing pipeline of surface I/O augmented interfaces that allows rapid prototype and iteration, and frees designers from the limitations of mechanical mechanisms. We prototype 35 distinct surfaces that explore the interesting facets of surface I/O, evaluate the efficacy of primitives and functional associations of exemplar designs through user studies, then detail key findings and design guidelines. To assess input accuracy, we built and tested a machine learning classifier in a separate evaluation. We also performed a baseline wear test of our microscale input features. We conclude the paper with several illustrative example interfaces demonstrating the potential and feasibility of the approach. Please see the paper for details. Thank you.